All right, another way to think about it with logarithms is if, say you had, let's say we had the log 2 of 8. All right. So the way we would say this is log is basically said 2, what is the power of 2 that's equal to 8? So in other words, if the base is 2, what power would give us 8? That's how we evaluate a log. The way we say it is, what is the power of 2, or base 2, if you want to say it that way, that equals 8? So what do we raise it to get 8? 3. 2 cubed is equal to 8, so that means log 2 of 8 is 3. So if I gave you log 3 of 81, what would that evaluate to? Look at your power chart if you need it. So if the base is 3, it's what power with a base of 3 would give you 81? Not 3, it would be 4. 3 to the 4th is 81. What about log 5 of 25? So what is the power of base 5? Or given base of 5, what is the power that equals 25? 2. So essentially a logarithm is just a very fancy way to write out an exponential equation, but instead of writing it like 5 to the x is equal to 25, they write it like this, so you can evaluate it. All right. And again, if you don't remember that setup, just remember you can always set it equal to x, do loggy froggy, and then do same base. All right. So yeah. And remember, with loggy froggy works like this. All right. So remember, you always start wherever the base is. So right here. Then you're going counterclockwise. So your first hit is this 2. Second hit is the equal. Third hit is the x. And then you write it in the order of b to the x is equal to y. So 1, 2, 3, 4. Those are all your hits. So first hit is where? The 3, right? Where's my second hit? 2. Equal signs my third hit. What's my last hit? X. And that's how you use loggy froggy. And if you're going backwards, it's the same thing. So if you had 2 cubed to the 8th, start at the base, go boom, 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 boom. So the log of 2, because that's my first hit, would be 8 is equal to 3. You can undo it. You can undo it and redo it. Now, the biggest thing is that if you're using loggy froggy, you've got to make sure that your exponential or your base, basically you got to make sure your base is on the left side. So if it was written like this, don't do loggy froggy like this. Because it gets confusing when you start going backwards. Just take the time, rewrite it so it looks like this. That's exactly the same thing. You just switch which side stuff is on the equal side. All right, so you want your base on the left side of equals for the easiest loggy froggy experience. All right. Any questions on any of this? All right. So the reason I'm bringing this up is today. Do you guys remember how I said when we were learning about solving exponentials with same bases? Do you remember how I said this only works in certain cases? Well, today we're going to learn about the case where we can't do that, and that is solving exponentials with unlike bases. Now, I said that we would put a pin in it and come back to it. We are now taking that pin out and talking about it. So, with unlike bases, the reason that we didn't teach it when we first taught it was because when we taught same base method, we didn't know about logs yet. With unlike bases, logs are your key. All right? Logs is the way that you solve it. And for these, you don't really get a pretty answer. Same bases usually give you a pretty answer. Unlike bases, they're never a nice answer. So again, the reason I asked you to grab a calculator is because that's basically how you get your answer. A lot of it goes in the calculator. All right? So again, we're on page 23 of your packet. So we already talked about methods of common bases to solve exponential functions. All right. So for example, if I had 2 to the 2x is equal to 64. How would I solve that? Who remembers? So method of common bases, what's the goal? So we're doing a method of common bases. We learned this Tuesday, I believe. What's the goal? How can we solve? We first got to do what to both or one side? What's the whole name of the method, guys? A common base. We need to find the common base. All right. So 64 and 2, when raised to different numbers, will have the same base. All right. What do you think the common base is here? And that's where your power chart comes in handy. So what's the common base? What number raised to specific powers would give us both 2 and 64? Right. Your base would probably be 2. So 2 and 2. And this is already raised to the 2x. 2 raised to the what is 64? So look at your power chart, guys. 2 to the 6 is 64. Now, what did I say happens when you have the same base? They cancel and you bring down what's in the exponent. So this is 2x is equal to 6. Divide by 2. X is equal to 3. All right. And that's how you would go about it with same bases. Now, unlike bases, basically, you'll see an equation where there is no way on God's green earth you will ever get a same base. All right. And that's when we have to use the log method. All right. So before we even do that, we gotta know about one of the logarithm laws. So just like with exponents, logs have their own special set of rules as well. The one that's going to help us the most with the same base technique, or not the same base, with solving exponential equations is this log right here. It's called the third logarithm law, or the power log, or the power law. All right. And all it states is that if you have log of some base equal to a raised to a power, if you have a power within those parentheses of a log function, you can take that x and bring it down to the front. So it would become x times log b of a. So essentially you can move that x out of the exponent. So with logs, if you have exponents within the parentheses, you can move it out of it and multiply it to the log. All right. Now, that being said, we're first going to do a very simple example that you can use same base for. So, but we're also going to show the logarithm approach as well. So just something to note. is that the log approach works for any exponential equation. So if you don't remember how to do same base, but you know how to do the log approach, that will work for any exponential equation, whether it's same base or not. However, same base only works for numbers that you know have a common base. All right, but the log approach can work for any exponential equation. So we're first going to solve 4x equals 8 with the method of common bases. So look at your power chart. You're looking at the columns specifically. For what base do 4 and 8 appear in the same column? So for what base do 4 and 8 appear in the same column on your power chart? For 2. So we're going to convert this to 2 equals 2 of something. And remember that x is still in the 4x. So we're going to put that on the outside so we can do power rule. 2 to the what power is 4? 2. 2 to the what power is 8? 3. Now, before we get rid of our bases, remember we got to multiply the x to the 2 in the exponents by power rule. So this would be 2 to the 2x is equal to 2 to the third. Now, the bases are the same. We can get rid of them. So we get 2x is equal to 3. Then to solve, we just divide by 2. X is equal to 3/2. Now, that was with the common base approach. We can do that same approach, but using logs. All right. So the logarithm approach. All right. With the logarithm, yes. So with the logarithm approach, there are 2 types of logs that you typically use. So the 2 types of logs that we're going to use for the logarithm approach is we can either use the common log, which is just log of x. So what's the base of the common log? Who remembers? 10. So remember, common log is log base 10. Or you can use the natural log. Who remembers what that base is? Not 10. That's common. I'll give you a hint. It doesn't sound like it's a number. E. So natural log is base E. So natural log's base E. Common log is base 10. In this class, you'll mainly use the common log, but I'm mentioning that you can also use ln because when I learned this, I learned it using ln. So forgive me if I accidentally start doing ln. I'm just saying that you can use either one, all right, and get pretty much the exact same answer. So again, it doesn't matter which one of these 2 that you use as long as you're consistent. So if you use common log, you got to use common log throughout. If you use ln, you got to use ln throughout. And again, it doesn't matter which one you use. I typically go for ln just because that's where my math brain likes to go. And there's special reasons for that besides the way I was taught. But again, for this class, common log is usually what you guys are going to use. So with the log approach, we're going to set up the exact same problem. So 4 to the x is equal to 8. Now, we already know that these are common bases, but we're going to pretend that they're not. The way you take care of this is that you will take the log of both sides. So we're going to take the log of both sides. So this would now be log of 4 to the x is equal to log of 8. And again, I'm using common log for this one. Now, through our new rule that we just learned, our goal is to get the x out of the exponent. So, given our new rule, which is the third logarithm law, or the power law, if you want to call it that, we can take this x and move it to the front of the log, and now it's outside of the exponent. So this would be x log of 4 is equal to log of 8. Now, think back to when we were evaluating logs. Is it not true that the log of 8 is going to give you some number? If we put log of 8 in our calculator, will that give us a number? Is it true that log of 4 is just some number? Yes. So essentially, if we're multiplying a number to x, how do we get rid of it? So log of 4 is just some number. It's not going to be a pretty number, but it's some number. So we're multiplying a number to x, and we need to get x by itself. How do we get rid of that number? Divide by it. So we would divide both sides by log of 4. This goes away. And what we're left with is x is equal to log of 8 divided by log of 4. Now guess what? This is a number. The entirety of this is a singular number. This is a number. So guess how we get it? We put it where? What's something that we have used to do things that we don't want to calculate on our own? The calculator. All you got to do is put this bad boy in the calculator and you get your answer. So, in your calculator, so this is why I told you need a calculator. So, in your calculator, we're going to use the log key, so the one that's right to the left of 7. So to the left of 7. So we're going to do log 8, close the parentheses, divided by log of 4, close the parentheses. Make sure you close those parentheses or it'll screw it up. And then hit enter. And we get 1.5. Now, what's 1.5 as a fraction? How do I do it to find it if it's a fraction? Well, we know it's 3/2, but how do I find it in the calculator if I didn't? Math, enter, enter. It's 3/2. Now, this was a nice one. More often than not, your answer will be an irrational number. Unless I state otherwise, so when we get into some of the other ones, unless I state otherwise, let's say round to 2 decimal places, so round to the nearest 100. Unless it gives you a nice answer that you can get like that. And yeah, the fraction's a nice answer. That's how you know they're messed up, if the fraction's a nice answer. So this is still 3/2. So 2 different approaches, we get the exact same answer. So the biggest thing that confuses people about the log approach is that a lot of times when they get to this step right here, so what's in the light green right here, they forget that just because it says like log, like the word log and then a number, they forget that that's actually just a number. All right, they think that since it has that fancy log word in front of it, it's part of some equation or connected to the x. In reality, this is still just a number times x, just like if we had 2x equals or 5x equals or 1/2 x equals. This is just log of 4x is equal to log of 8. And to get rid of it, we would just divide it over. All right. Now, that was just to show that either method works. All right. And again, the logarithm law removes any variable from the exponent. That's why we want to take the log of both sides, because we want to get that variable out of the exponent. And the only way we can do that is by using either common log or natural log.
Honestly, you can use any type of log as long as the bases are consistent. But typically we use either common or natural. Like either one would work. So like for example, if I just did the natural log of 8 divided by the natural log of 4, I get the exact same answer. All right, it doesn't matter what type of log you use as long as it's consistent. You can use natural log, you can use common log, you can use log base 3, log base 2. Any type of log will give you that same answer. Yes. But when in doubt, just use either common or natural. And again, it doesn't matter which one. But for this class, you mainly use common. So this law in combination with logarithm base 10 or the common log allows us to solve almost any. So we can solve almost any exponential equation using calculator technology. So you definitely need a calculator for this method. Because if I want to give an approximate answer, you'd have to put it in your calculator. Because obviously some of these logs are just not rational numbers, meaning that they go on forever and ever. So we're going to use the log method to solve these next couple of problems. And we're going to round it to the nearest hundredth, and you'll see why in a second. Now, let's look at this. 5 and 18. Is there any common base that could be pulled from those two numbers? That's what you should ask yourself when you see an exponential equation. Can I make a common base? If not, we use the log method. Can I make a common base here? Yeah, there's no possible way. The next step up from 5 is 25, which is over 18. All right. And 5 doesn't fall in any other bases below it. So there's no common basis, so we have to use the log method. So again, my very first step is to just take the log of both sides. You can do that just like you can multiply something to both sides or divide something from both sides. As long as you do it to both sides to keep it balanced, it's completely fine. So we now have log of 5 to the x is equal to log of 18. Now, I need to get the x out of the exponent. What did I say I can do? How do I take care of that x in the exponent? We bring it down to the front. So this is now x log of 5 is equal to log of 18. Now what do I do? What's my last step here? Divide by log of 5. So we're going to divide both sides by log of 5 to get that x by itself. Goes away. X equals log of 18 all over log of 5. Now, if I asked you for an exact answer, this is where you would stop. So this answer right here is the exact answer for x. That means we haven't put in our calculator. There's no rounding involved. That's what our answer would be. However, I want an approximate answer. So if you ever give me an approximate answer or a rounded answer, you have to write squiggle equal sign. Because, and again, I won't take off points if you don't, but at the same time, you need to. Because what this is saying, this sign means it's exact. Equal sign means it's exactly this. This sign means that it's approximately. All right. It means that we rounded it. It's not the exact answer. We took some of that answer off. So put this in your calculator. Tell me what you get. And round it to 2 decimal places. So put that in your calculator. Tell me what you get. So do log 18 divided by log of 5 in your calculator. So I should see a lot of clicking keys. So did anyone get an answer? Haley. 1.8 and you did it in 2 decimal places? Yeah, so 1.80, let's call it that. So the approximate answer would be about 1.80. So again, it depends on what I ask for. If I ask you to give the exact answer, and if you put that in your calculator and it does give you a pretty number, just leave it like this if I ask for the exact. But more often than not, I'll ask you for the approximate, and this is what I want. All right. But more often than not, you're going to have the exact answer somewhere in your work anyway. Any questions on that? All right, let's try another one. So let's try letter C. So, first step, what do we do? Take the log of both sides. So this is log of 2x, raised to the x equals log of 1560. Someone else, what do I do now? Who has not talked today? Right, we move the x to the front. So this is now x log of 2 is equal to log of 1560. What's my last step? Divide by log of 2. Good. That goes away. We get x is equal to log of 1560 all over log of 2. Go ahead and put that in your calculator. Tell me what you get as your approximate answer. So x is approximately what? Rounded to 2 decimal places. You're fine. Page 23 of your note, of your packet. So if you input in your calculator, remember, you would hit the log key, which is to the left of the 7 on your calculator. So log of 1560, close the parentheses, divided by log of 2, close the parentheses. So you should get about 10.61. So your answer will be approximately 10.61. And again, make sure you use that squiggle equal sign. Now, those are actually some fairly easy uncommon bases because the base is already isolated. All right. So do you guys remember when we were doing absolute value equations and I said we can't break it into 2 equations until the absolute value is isolated? Same thing with exponential equations. You cannot take the log until the base itself is isolated. All right. And that's where a lot of these come in. Or there's another one, but these have like, yes. Yeah. The bases are still isolated, yes, but you got to do a little bit more work afterwards. So let's look at letter A of exercise 3. So the base is already isolated. All right. We already have one base. There's nothing else outside of it except what's in the exponent. But the exponent is a little bit different. Instead of just a straight up x, we have x plus 3. Now, that doesn't really change anything rule-wise of what we're going to do. It just means we're going to add one more step at the end. All right. So we're still starting off with the same process of taking the log of both sides. So this will be log of 6 raised to the x plus 3 is equal to the log of 50. Now, what's typically my next step here? What do I do? Right, we just bring the exponent to the front. Bring the entirety of the exponent to the front. So bring this entire x plus 3 to the front. I would write the x plus 3 in parentheses when the log's still attached to it so you know that that's attached. So x plus 3 log of 6, because we're multiplying that log of 6 to the entirety of x plus 3, hence the parentheses. is equal to the log of 50. Now, again, the reason I put that x plus 3 in parentheses is because since it's being multiplied all together by the log, the x and the plus 3 are married. You cannot break them apart. Yeah, they're married. You cannot break them apart. Log of 6 is a third wheel. They want to get rid of that third wheel before they can do some divorcing. All right? So, yeah, it's a complicated relationship. There was already a threesome, and now they got to get down to it. I mean, come on. Like,
we're getting somewhere.
I mean, hey, sometimes you got to put things in ways you understand. So we got to get rid of the third wheel here. And we get rid of it just like we've been doing it. We'd still divide by log of 6. All right, so we're dividing both sides by log of 6. So that goes away. We're left with the x plus 3. And then we have log of 50 over log of 6. Now, don't put that in your calculator just yet. Because what do we need to do here? What's left? There's the x needs to be by itself. It's ready to go back to its bachelor days. All right. So how does it get rid of that nagging 3? You subtract it by 3. So we subtract 3 to both sides. This goes away. We get x is equal to the log of 50 over the log of 6, all minus 3. So if it helps to remember that's all minus 3, put that in parentheses. Now we put all of that in our calculator. So you can either do it in one shot, or if you're kind of worried about it, just do the log part first and then subtract that answer from 3. So I'm going to break it up. So I'm going to do log of 50 divided by log of 6. Hit enter. And then immediately after that, I'm just going to hit minus, because what it does is it takes my previous answer and inputs it 3. So I'll get about negative 0.82. So x is equal to negative 0.82, or approximately. Even Miss Murphy used the wrong sign. All right. Oh yeah, the x was the 3 cheated, so they were moving in with the other guy. So yeah, there was another woman. All right. Any questions on that one? All right. Let's try another one. So, letter B. Since the base is already isolated, all we're left with, there's nothing outside of it or being multiplied to it or nothing. We can go straight into the taking of the log. So we log it on both sides. So this is log of 1.03 all raised to, and this is kind of hard to see, but it's actually x over 2 minus 5 is equal to the log of 2. Now, what's my next step here? We got to bring the entirety of the exponent to the front. So this would be in parentheses x over 2 minus 5 log of 1.03 is equal to log of 2. What's my next step here? Right, we divide by log. We got to get rid of that happy marriage. Hey, I guarantee y'all will never forget this lesson. All right, so the log's gone. So we're left with x over 2 minus 5 is equal to log of 2 all over log of 1.03. We're not done though, because we got to get that x by itself. So now we're thinking about how we solve basic equations. So what's my next step here? Not quite. Jasmine, you were on the right track. Add 5. So the reason we don't multiply by 2 just yet is because the 5 is not also over 2. So we got to add 5 to both sides. So we get x over 2 is equal to log of 2 all over log of 1.03 plus 5. Then we multiply by 2 like Landon said. Shh. Multiply by 2 to both sides. Make sure you put that entire expression with the log of the plus 5 and you're multiplying 2 to the entirety of it. So that goes away. And we get x is equal to 2 times log of 2 all over log of 1.03 plus 5. Now, be very careful how you put it in the calculator. I would do like a breakup because I'll honestly like break it up and then just keep adding and multiplying stuff to it, because a lot of times if you try to put it all in, parentheses will be your downfall. Trust me. All right. So I would start, if you're putting in the calculator, start with this. So start with the log division, then add the 5, then multiply by 2. So if you did in your calculator, you would have log of, what was it? I already forgot it and I just saw it. Yeah. So log of 2 divided by log of 1.03. Hit enter. Add 5 to it. Hit enter. Then multiply it by 2. Because essentially that's what we did. It took care of the parentheses first by PEMDAS. We did the division within the parentheses first, then the addition. Then we did the multiplication that was outside the parentheses. Again, you could put it all in your calculator and get the exact same answer. But again, you would have to use a lot of parentheses for that to kind of make sure that your calculator does everything in the right order. Because your calculator is a great tool, but depending on how you put it in, your calculator can also be really stupid. All right. So I always say your calculator is as smart as how you put stuff in. If you put something in that doesn't compute with them exactly, they're dumb. All right. So this would be about 56.9. And that would be your answer. And again, if I asked you for that exact answer, you would give me all of this mess. All right. Just leave it like that, the green, if I ask for the exact. But approximate, that's fine. Any questions on that? All right. Oh, yeah. Here's now. Yes. Yeah. Now, you guys remember at the beginning of this unit when we did all those exponential growth and decay stuff, but we basically were only evaluating because we were always given the x value? Yeah, that's not happening anymore. They're only going to give us the y value now. We're going to have to solve for x. So we get to use the same process. All right. So we're revisiting some exponential models. I said it would come back to bite you, and it did. So again, this is the exponential growth model, where this is what you start with. This is typically your rate, which is given to you as a percentage that you have to turn to a decimal, and t is your time. Now, what we've dealt with so far when it came to exponential word problems is they typically already gave us our time unit, and we would put it in our calculator and evaluate it, essentially. We'd already get the equation, and we could just put it all in our calculator, bing, bang, boom, we're done. That's not the case here. All right? This time, they're only going to give us what our end result is, and we need to figure out how much time has passed. And that's where we're going to use common logs to help us find that. So same process of what we've been doing. So first things first. A biologist is modeling a population of bats on a tropical island. He first starts observing them. There are 104 bats. The biologist believes that the bat population is growing at a rate of 3% per year. So growing, exponential growth or decay. It's growth. So we're definitely using the top formula. So we're going to write an expression B of t that will represent what's going on. So we're not writing the equation to solve just yet. We're just writing a formula to help us figure out what's going on. So you need your principal value first, or your starting value. What did I start at? 104. And by the way, this equation is the same thing as A is equal to P times 1 plus R to the T. That's probably the way you're used to seeing it. Same exact thing, just different letters. Yeah. So that's our start. What's our rate of growth? 1.03. So 3% is our rate. So that'll be our R value, but we need to convert it to a decimal. So it'd be 0.03. And we pretty much got everything we're going to fill out because T is still our time, but we don't know what that is. And we don't know what B of T is either. So we get B of T is equal to 104 times 1 plus 0.03 all raised to the T power. Now, I'm not done yet with writing this equation because what else can I do? Where's one place that I can simplify? Right. We can do the 1 plus 0.03. So if I add those together, that's a really easy addition. It's just be 1.03. B of t is equal to 104 times 1.03 raised to the t. So most likely, we're going to be using that expression in some shape or form. All right. Now, the next thing that we're going to do is we're actually going to do some solving. So it wants us to know algebraically how many years it will take for the population to reach 200. So let me ask you this. Is 200 going to be my B of t, or is that going to be my t value? B of t, because remember, t represents the number of years that have passed. So 200 is actually my B of t. Now, that means I get 200 is equal to, because that's my B of t. Why are you like this? 104 times 1.03 raised to the t power. Now, this is where you got to be careful. Because first off, is my base isolated quite yet? So what is my base here? 1.03, yeah. So 1.03 is my base. Not 104, sorry. I didn't hear you quite. So 1.3 is my base because that's what's connected to the exponent. All right. Your base is what always is connected to your exponent. But is it isolated, meaning it's alone? No. What do I have to get rid of in order for it to be isolated? The 104. How do I get rid of it? We would divide it. That 104 is being multiplied to the 1.03 of t. So we got to divide both sides by 104 to get rid of it. We cannot take the log yet until that base is isolated. So this goes away. So this becomes 200 over 104 is equal to 1.03 all raised to the value of t. Now guess what we can do? So this looks familiar now. Now what can we do? What have we been doing? We can take the logs of both sides. Once that base is isolated, there's nothing else connected to it, we can take the log of both sides. So this is log of 200 divided by 104 is equal to log of 1.03 t. What's my next step from here? What would I do up here? What was I doing up here when I was trying to figure out the log stuff? As soon as I got to this state, what did I do next? Nope. I got to do something with my variable. What do I need to do?
Move the t to the outside of
Right.
the log.
We got to move the exponent to the front of that log. So it's the exact same thing that we've been doing, guys. It's just written on different sides of the equal sign. So don't let that throw you. So this is log of 200 over 104 is equal to t log of 1.03. What's my next step? Or is my last step actually? I need to get the t by itself. How do I do that? Right, divide the log of 1.03 to both sides. That goes away. I get t is equal to log of 200 over 104 all over log of 1.03. Now, it says to round our answer to the nearest year, so we're going to have no decimal places when we put this in our calculator. So in my calculator, I'm going to do log of 200 divided by, what was it, 140? Or no, 104. Divided all by log of 1.03. So about 22 years have passed. So t in this case is approximately 22 years. And make sure you put your units. So again, same process, just different context. Now, when you're doing the EOC, you probably will forget all about this by then because you still got a couple months. The easiest way to do this if you forget, and honestly, if this is like a multiple choice question on the test, by all means do this method. The hardest part that you have to remember is just how to get this equation. If you can get that equation, it's really easy to figure out the rest because all you got to do is, if I have Desmos open, I'm going to type in the function that I have. So y equals 104 times 1.03 all raised to the x power. Now, 200 is what we're shooting for. Would that be an x or y value? So let me ask you this. We already said 200 is b of t. Is b of t in the place of y or is it in the place of x? When we typically write an equation, is it typically y equals or x equals? It's y equals, right? Right. So y is equal to 200 because our population is our output, which is 200. Now, guess what? Zoom out a lot until you start seeing the graph. What do you think my answer? Where do you think my answer is going to be on that graph? The point of intersection. Now, what value of that point do I use as my answer? The x value, because we're solving for x. And just like that, no math involved, your calculator did it for you. The worst part that you have to do is that you just have to figure out how to write the function. All right. If the actual solving gives you crap, put it in Desmos. Now, I still expect you to know how to do log method, but say if this was a multiple choice question on the test where it's right or wrong anyway, so I don't necessarily check work for multiple choice questions. Short answer is really all I care about with work. But multiple choice, like, you know, you have Desmos access to you in the entire test. Like, I know y'all are not going to be math geniuses, and that's okay. You just got to know how to use the tools to your advantage. All right. So if you can do this and you know to find a point of intersection, you're golden. All right. Any questions on that? Do I need to do another one or do you guys feel pretty good? All right. I just want to do one from exercise 6 just because it is a little bit different. Yeah. So exercise 6 really quickly. Is my base isolated? What is my base? 2 is my base. So that's right here. Is it isolated? No. So I need to isolate it first before I take logs. So what would I do first? Add 3 to both sides. 4 of 2 to the x is equal to 20. Is it isolated now? No. What do I do? Divide both sides by 4. 2 to the x is equal to 5. Now I can do business as usual. Take the log of both sides. So I get log of 2 to the x equals log of 5. Bring the x to the front. This is x log of 2 is equal to log of 5. And then divide both sides by log of 2. So x is equal to log of 5 over log of 2. And you could give me an approximate answer, but I'm just going to leave it like that. Because obviously you'll put that in your calculator, get an answer. But that's all I really care about right now, that you can at least do the math. Now, if this was given to you in your calculator, all right, and you forgot how to do it, all you do is break apart the 2 parts of the equal sign, and you put both of them equal to y. And then you graph that in Desmos. So in Desmos, I have y is equal to 4 times 2 raised to the x power, what was it? Yeah, minus 3. And then I got y is equal to 17. Let's find that point of intersection, which if I zoom out, 2.32 is my answer. And is that about what you got approximately after we solved it? Yeah? That's another way we could have solved it. So again, guys, there's a lot of methods to get to this answer. On the EOC, trust me, they don't give a crap how you solve it. They just want the answer. And you have Desmos for the entire test. Use it to your advantage. Because I know this stuff can be hard. All right? I've been doing it for years. That's why it looks like I can do it like in a snap. But again, I've been doing it for years. But you guys haven't, and it's totally fine. And you'll probably forget this by the time of the EOC. The hardest part is figuring out where to start. And a lot of times, you can put stuff in Desmos and it will save your butt. All right? I can tell you right now, last semester, a lot of my kids in that class, it was a regular class. Almost all of my kids passed the EOC with a 3 or higher, which a 3 is passing. And they were regular kids just like you guys. But they used Desmos or standard class, I should say. But they used Desmos to their advantage. And I will teach you the tricks of the trade. Don't worry, I will teach you. All right? I'm going to teach you, so throughout this class, I'm going to teach you both the math as well as the trick in Desmos.
So I think it's important that you guys know it because I want you guys to pass. All right. And that EOC is a good factor in whether you pass this class or not. The other part is actually doing your work. All right. All right. Any questions on any of that?
All right. So you do have a delta math for 2.4. It combines the common bases as well as the unlike bases. That should already be available to you. You only got about 15, no, it's more like 10. You only got about 10 minutes left of class. So if you want to start it, that's great. If not, there's your exit ticket. Yeah. Ah, crud.